Okay, real quick announcement before we get into the math. I've gotten several questions from students about attendance stuff. Where's the Canvas site? I don't have the attendance quiz. Oh my God, right? So I guess I should have been more clear in what I wrote on the website, but the attendance stuff doesn't even begin until after the class roster has settled down. It's definitely not this week. Possibly next week at some point. My best guess would be probably late next week would be the earliest that I would begin that. So so for the moment, the Canvas site doesn't even exist. Again, related to it doesn't make any sense for me to make a Canvas site and then have to fiddle with the roster as the enrollment changes. So there's that. Then I'm also going to point out, likewise with Gradescope, I haven't created the Gradescope site yet. I'm waiting until, again, I'm hoping the roster will settle down as much as possible so I can get as many people automatically added when I first create the site, as opposed to having to go in manually and add, drop, add, etc. as the enrollment changes. So anyway, there's currently no Gradescope site. It'll be created probably tomorrow. Okay? I will send an announcement when I create it. You'll probably also get some sort of automated announcement. I don't know, but anyway, Gradescope will be created probably tomorrow, no promises, but certainly before our first homework due date, which of course is Sunday. Okay, so back into the math. So last time we just kind of scratched the surface of this example here where we have a wheel that's rolling along the x-axis, like the x-axis is the ground, right? And radius A, blah, blah, blah. We have a reflector sitting right here on the wheel. And the idea is as the wheel rolls, that reflector will move, and it's going to make this kind of scallopy pattern that I'm sure y'all have seen when bicycles, ride underneath street lamps at, dusk or later. Okay. So the question is, how do we parameterize that path? So the big idea is that this reflector, which is going and doing stuff like this, at any given moment, where it is at any given moment, is a sum of simpler things. This is what we talked about last time. It's a sum of where is the axle. Let's see here, I should go with it. So the reflector is wherever the axle is plus what you might call a spoke, right? So this little displacement from the axle to the edge of the wheel, like so. So blue plus purple, right, gives me where the orange reflector is. Does everybody buy it? Okay, so all we got to do is figure out how to parameterize. How do we identify where A is as a function of time, and then how do we identify what that purple D vector is doing as a function of time? Okay. All right. So that noted, let's take one at a time. Here's my axle. Not hard to see that this is what it does. All right. That's why the frame of the bike attaches to the axle, because it stays nice and level, right? So you're not constantly bouncing up and down as the wheel moves. So, okay, how do we describe that motion? How do we describe what how A moves as time passes? So, before we can get to that, what we have to do is decide how are we going to define time? Where is time equal to 0, for example? And in fact, I should stop saying time. Let's just say t. I mean, you can kind of think of it as time, but I don't want to get into the weeds of what's the speed and distance per unit time. We don't need any of that. So, what is t? What is the parameter with respect to which I want to compute a and d, and therefore p? And there's different ways to go about this. I think a very reasonable choice is to use this angle that you can see I already have drawn in here. I think that's a very reasonable choice for t. I emphasize the word choice. We don't have to do that. We could define our parameter to be some other player in this story, but I think that's a reasonable choice because, now this is just an appeal, when we start, that angle is 0, and kind of a reasonable thing to think that, yeah, maybe we start when time is 0, right? I mean, it's a natural choice. And then furthermore, as the wheel rolls, as time passes, this angle increases, just like time does, right? So it's natural in that sense. Does everybody see it? Everybody buy it? Okay. Now, I can't emphasize enough, I chose that. I don't have to, right? So when you choose parameters, when you're doing your own parameterization of curves, be careful and thoughtful about your parameter. Don't just reflexively choose, well, I'm always going to choose the angle theta or something like that, because you might end up with something that's ultimately kind of unnatural. Okay, so there's my parameter. That's t, and with that noted, first question, where is this axle at time t? Let's take one coordinate at a time. What is the x-coordinate of this point? The x-coordinate of that point, this distance, I'm going to try to figure out. And then here's the argument I'm going to make. This is a subtle argument. It's a physical appeal. By the way, I'm going to have to do a certain amount of physical appeals. I claim the world works this way. I hope that seems plausible. Right? And then likewise, some geometric appeals. Sometimes you can look at the picture and you can get some satisfaction that will, of course, blah, blah, blah. So physical appeal, the amount of road that has touched rubber, right? The rubber started touching there, and the rubber to this moment is to here. The amount of road that has touched rubber equals the amount of rubber that has touched road. Oh, I did that. Oh, man, let me do that again. So the amount of rubber that has touched road is equal to the amount of road that has touched rubber. Again, physical appeal, right? I claim this is another way of saying the wheel isn't skidding along the pavement, right? Does that seem reasonable? That's the big physical insight that's going to make the solution possible, because I know that my x-coordinate is what I have in light green here, and I just argued that what I have in light green is equal to what I have in dark green, and what I have in dark green, here it goes, dark green. What I have here, that is an arc of a circle. And flashbacks to high school geometry, y'all know how to compute the length of the arc of a circle. It's the central angle, which in this case, very handy, we've set up to be t, right? Central angle times the radius, and we've set up the radius to be a. So, AT. Everybody happy? Clever little argument. But there you go. And ultimately, pretty easy. By the way, I'm going to say a freebie as to what the y-coordinate is, because again, the axle has a constant y-coordinate. It's clearly a. Okay. All right, next. Now we've got to focus on... Oh, wrong color. Sorry, I hit the wrong button. We've got to focus on that vector, right? Is what I'm calling D. So how does that vector behave? Now, a common mistake that a lot of students make is to think, ooh, that's going to be hard because that vector is doing like this, right? And you feel like it's not only turning, but that it's also moving. So let me remind you, vectors, when you're thinking of them as vectors, in other words, as a direction and a magnitude, that's what a vector is. They don't have location. There is no location. Right? The arrow that I use to represent a vector has a location because I have to draw it. There it is, right? It's the ink on the page is that in that spot. Arrows are a clumsy tool that we use to represent the real mathematical object of interest, namely the vector. Direction, magnitude. There is no location. So with that in mind, that purple vector, I can just as well, if I can get this to behave, there we go, I can just as well think of that as having its tail at the origin, because it doesn't have a location in the first place. I am going to draw an arrow there instead. It's easier to work with. And what can I say about this? Well, it's pretty straightforward. I mean, there it is, cosines and sines, right? I mean, this angle, theta, that vector is located at a cosine theta, a sine theta. And, I mean, we're almost done with that analysis. Little micro annoyance that we have to deal with. The goal was to write everything in terms of one parameter. We've already decided that parameter is to be t. So I need to write this in terms of t, not theta. And so I have to figure out how to rewrite theta as a function of t. Is everybody with me? Okay. So how do I rewrite theta in terms of t? This is actually a pretty easy pitch. That theta, there we go, do it like this. That theta, and I believe I used red to be my t. This t have a nice easy relationship that t and theta, they always add up. Oh gosh, color choices. I'm out of color. I'll use dark blue. They always add up to 3/4 of a turn. Right? They always add up to 3 pi over 2. I get geometric appeal. Right, so if t plus theta is 3 pi over 2, then I can solve for theta as I have here. I can take that theta and plug it into there. And then I can take my d vector that I'm interested in, that I already know is that formula. And then I can, let's see, well now I have to use angle addition formulas for sine and cosine. By the way, that's one of my, I'm going to call it a pet topic. I think it's underappreciated. Somebody made a decision in high school trig classes, I don't know when, maybe 10 or 20 years ago, that students don't need to know that anymore. Well, students who come and do engineering at Duke 100% need to know those formulas, and so high schools have not served us well there. You need to know the angle addition formulas. For sine and cosine, just sine and cosine. Don't worry about trig and cotangent and stuff like that. But for sine and cosine, and use those formulas, and you can rewrite d in terms of t. Yes?
How do you know that theta equals 3 pi over 2?
Yeah, because I know that green plus blue adds up to 3/4 of a turn. Does that make sense? Yeah. Yeah.
And you chose 3 pi over 2 because the reflector starts at the bottom?
Yeah, I'm going to quibble with your language a little bit. By the way, I mean no offense, but so I didn't choose it, right? I defined t. Maybe I chose my definition of t because the way I did because of it started at the bottom. But 3 pi over 2 is imposed upon me by the geometry. Is that cool? Yeah. So boom, we're in business, and if I can get this thing to cooperate as we previously agreed. Now we've gone through a bunch of details here, blah 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 details, but the location of the reflector, tracing out that path. So I guess I can squeeze. Oh, and I can go full screen too. Is therefore this, because the axle we solved for there, and the d vector we solved for there. So not that bad, as it turned out. There's, again, a couple little details you got to worry about, and trig and formulas, and worrying about choices of this, that, and the other thing. But ultimately, blue plus purple is orange, and now we have a parameterization of our curve. So ultimately, who gets the credit? Like, what's the big takeaway? What's the big lesson from this example, aside from, pay attention to the details? Is vector algebra is wonderful, right? This was the foot in the door right here. Being able to say that this complicated curve that doesn't even look familiar, I don't even know what that thing could be, how strange, is a sum of much simpler things. That's the big win here. Okay. All right, moving along. Here's another example. Actually, kind of similar lesson. How do I parameterize a line? Well, I'm going to approach this in a way that's not that different from what we did with the bicycle reflector. Namely, I'm going to say, look, as I trace out that line, if I look at some point on that line, I can always view that as being, well, some starting point. Oh, good, I was given a starting point. We're given R0, right? Plus some vector parallel to the line. Right, so looking at this picture, how can I write purple? Well, it's green plus blue. Right? And again, the green was given. And that blue vector was not given, but what I was given is a vector parallel to the line. And, well, if that vector is parallel to the line, then any other vector parallel to the line is a multiple of it. And so, here we go, light blue. So... And by the way, why did I choose T as my multiple? Why didn't I use K or C or something like that? Because I could kind of see it coming that that's going to be my parameter. That's what's going to give me position as a function of. That's effectively the variable that goes into this function. And I know that I like my input parameters to be T. So, thus, yes.
Why did you put the little arrow over R0?
Right. No, that's a great question. So yes, it is important to be aware of the distinction between points and vectors. They are definitely different things.
Yeah.
However, it is extremely convenient to conflate them in situations where the context will make it clear what you're talking about. Right. So very commonly, people will use vectors to represent points because, well, I mean, look, if you'd like, I mean, I can draw the little arrow here, right, that represent, tail at the origin, head at the point, and there's the vector. But when I write it as a vector, but say interpret it as a point, it's implicit that that's what I mean. Is that cool?
Okay.
And then likewise, vice versa. Sometimes we'll use points to represent vectors. It's just convenient. The alternative would be that I would have to set up not only a vector algebra, but a points and vectors algebra, right? And I don't want to have to write down a whole new formula for what is point plus vector when I already have a formula for what's vector plus vector, and I can just interpret appropriately. It's a great question. So is everybody clear with that? I mean, it's very handy to kind of pass interchangeably between these interpretations as long as you interpret, validly, appropriately. All right. So that's how you parameterize a line. This next page, again, here's that header. This doesn't really quite rise to the level of what we can spend a lot of class time on, so I'm not going to do most of this page. Make sure to read it. I think these are a couple of cool examples. I think you'll find it helpful. I think it'll help you understand the ideas. Keep in mind, there's a lot of stuff that we're not going to do in class that I think is still, even though we can't spend the class time on it, still, educational, good learning experience. And so I hope you'll take the time. And I hope this will be helpful to that end. I will say a couple of words about this business. And that is, it's very important to distinguish between a parameterization versus an equation. They are algebraically pretty different critters. Like how a parameterization describes a curve and how an equation describes a curve. Very different. As follows, I mean, look at how, what does a parameterization, have to do with a curve? Well, the parameterization takes in a parameter and spits out a point on the curve. No matter what t you give me, it spits out a point on the curve. So the curve relates to a parameterization in that it's what comes out of the parameterization. That's not what equations do at all. equations are kind of the opposite. Equations say, oh, you have a point? You want to know if that point's on the curve? Oh, okay, well, tell me the point, tell me the x and y. We'll plug that into our equation. And you'll either get a yes, that the equation worked, that means the point is on the curve, or the equation will not work, that means the point is not on the curve. So I like to represent this distinction as parameterizations are point generators and equations are point testers. And you just got to always keep in mind what you're looking at. Think through what is this algebra that I have before me and interpret it appropriately to what it is. Right? And here's the really frustrating thing to me. This is a constant frustration for me. There is an alternative word, an alternative phrase for describing a parameterization. It is parametric equations. They use the word equation, which conflates these two things that we need to keep distinct. They are mathematically very importantly different things. So the only time you'll ever hear me say parametric equations is to talk about how I don't like the phrase parametric equations. But they're very common. You're going to hear them, and please just roll your eyes every time you see that. And please, I encourage you, think parameterization. Keep that distinction. Okay, so this is one of the big ideas behind this example. Again, part of what we don't have time to go through the details of. I think it's a pretty straight read. I think both of these are pretty straight reads. So take a little time. I think they're good examples. Okay, this one is a little tricky. I'm going to talk through this one. What if we want to do a line in R3? Parameterizing a line in R3 is just like parameterizing a line in R2. It's exactly what you would think it is. No big deal. But what if I want a point tester, right? What if I want something kind of like an equation? I don't want to generate points on the line. I want to test points on the line. How do I test points on the line? And here's the idea. If you have a line in R3, here's the parameterization. Right? You got a starting point. And then you've got parameter times your direction vector, just like in 2 dimensions, no problem. And what would be the test if I wanted to have a test instead of a generator? And this is going to sound like a cop-out. How do I test x comma y? How do I test if that point is generated by this generator? Well, the test is, does there exist a value of t that I can put there that makes the parameterization spit that point out? And now I have to explain my terminology notation here. This is actually pretty standard notation. This weird symbol here means there is or there exists. And this little weird looking symbol there means such that or so that. Very handy. There's certain little phrases that mathematicians say all the time, and it's very nice to have a little quickie little symbol so we can save some ink, or in this case, save some pixels. So again, silly test. Yeah, if there's a t that produces that point, then yeah, that point is produced by that point generator. Okay, so what am I going to do with this silly observation here? Oh, gosh. I'm going to rewrite this algebra by solving for t. And keep in mind, when you have a vector equation, this is actually 3 equations, right? There's sort of the first coordinate equation, and then the second coordinate equation, third coordinate equation. You might want to multiply, add, write that all out. Make sure you're comfortable that this is in fact 3 separate scalar, you might say, coordinate equations. And in those equations, if you solve for t, in the first equation you get that, in the second equation you get that, and in the third equation you get that. Okay, now let's reconsider our test. Test being, I need to know that there's a value of t that makes all of this work. Okay, well, let's say that differently then. I need to know that there is a value of t that makes all of this work. And now we're almost there. We basically have it at this point. I need to know there's a value of t such that t equals 3 different things. No, just intuitive appeal. How could t equal to 3 different things? You're telling me you want me to find a single value of t that's equal to 3 different things? Nonsense. Not possible. How could there be one number equal to 3 different things? It doesn't stand to reason. Well, I don't need these things to be different. I can have t equal to these 3 different expressions if, in fact, all 3 of these expressions, if all 3 of these expressions are all equal to each other. If they're all equal to each other, then yeah, there is a value of t equal to all of them because they're all the same. And whatever that same value is, that's what t is. Everybody good? So really nice how this works out. So what we end up with, again, is a point tester. You give me an XYZ. You want to know if that XYZ is on, whatever line that, starts at this point and goes parallel to this vector. Well, compute these 3 things. Make sure they're all the same. If they're all the same, boom, score. That point is on your line. If any 2 of these are different, maybe 2 are the same and 1 is different, or all 3 are different, or whatever, right? Anything other than all 3 of these being the same, that point is not on the line. Okay. So this is called the symmetric equations. It's a real clever idea. I like it. Very cool. And I wish we had more time to talk about it. Turns out there's some really cool observations that you can make about the symmetric equations and how that relates to certain planes. And fun stuff, but we don't have time. Okay. On to 1.3. So we're done with 1.2. So y'all remember dot product. I'm gonna mostly let y'all read and remind yourself. Y'all know this formula, right? It's huge in linear algebra. You know what the dot product is. It's got 1 million properties. Y'all have seen those 1 million properties before. Make sure you remind yourself of those. And real quick for your consideration, I'm sure in your linear algebra classes you saw this thing called an inner product, defining something called an inner product space, and that's really useful for some pretty sophisticated math. By the way, in case you're curious, one of the big tools of image compression, right? Where did that come from? Right? So image compression, one of the big ideas is learning how to write functions as linear combinations of other functions. How do you do that? Well, you may be having flashbacks now to linear. How do I write a vector as a linear combination of other vectors? And it turns out that if you have an orthonormal basis, then dot products will tell you those coefficients. And likewise, you can do this with other kinds of vector spaces. And there is a way to view functions as vectors in a vector space, and even functions of multiple variables as vectors in a certain vector space. And you could define something called an orthonormal basis for such a vector space. And then you can create a certain inner product, kind of like a dot product, but for weirdo vector spaces. You create a certain inner product, and you use the exact same formulas, and you can rewrite a complicated function as a sum of simpler functions. And that's basically how image compression works, or at least one of the big ideas in image compression. And lots of details as to how do you actually make that work. And by the way, for your curiosity, this is one of the major tools for this is called wavelets. Y'all ever heard of wavelets? No, okay. Wavelets were a breakthrough idea. Wavelets are how, for example, the JPEG system works, right? And wavelets are an orthonormal basis of this fancy inner product space. And the person who came up with the best, maybe not the first, but the person who made the greatest leaps in progress in study of wavelets is Professor Ingrid Dobeshies, who is a professor here at Duke. So we stole her from Princeton, by the way. So anyway, very cool. Okay, so big ideas there. I do want to talk about this. This is another one of my little quibbles. I guess I have a lot of quibbles. These two words very often get used interchangeably. I think that's unfortunate. I want to encourage y'all away from this. Now, I'm going to confess that, I was, mathematically speaking, I was brought up being sloppy. I was told at some point that orthogonal is just a fancy word for perpendicular. And I don't think that's right, and I don't think it's a good choice. I think this is just a straight up bad idea. And here's the reason. It's because there are two different ideas. There's this algebraic idea of a dot product being zero. That's arithmetic. Give me any two vectors, plug them in. The dot product either is or is not zero. All algebra. And then there's this related geometric idea of if you have two vectors, you look at the directions that they point, and you can look at the angle between those two directions, and you can talk about whether that angle is a right angle or not. That's all geometry. Directions and angles and stuff like that. The problem is that they make sense in different cases. You can't talk about the angle between two directions unless you are quite sure that the vectors actually point in directions, right? The zero vector does not point in any direction. Or you might say it points in all directions, right? It does not identify a direction in any sense. So if either of your two vectors is zero, I don't know what you mean by perpendicular. That's nonsense. Right? Not my fault. I didn't do it. I'm just saying, right? Whereas, if you have two vectors and one of them is the zero vector, okay, cool. Not only can I ask, what's the dot product and is it zero? I can even answer that question. The dot product is zero. Okay? So this makes perfect sense. This doesn't. So what that means is that we have two distinct ideas. They are not identical. And we also have two words to describe these two distinct ideas. It seems to me that we should use one word for one of the ideas and the other word for the other idea. So, again, I strongly encourage that you be fussy, like I am, about this distinction. They are different ideas, and it will lead to confusion, and you will get some wrong answers if you're too sloppy conflating these ideas. They're not the same. Okay, enough of that. Okay, lots to say about dot products, and again, tough choices, and oh my gosh, I wish I had 300 minutes a week to talk to y'all instead of 150 minutes a week, but here we are. So again, y'all are going to have to read most of this stuff. I'm just going to hit some highlights, again, as usual. So if you want to know the unique unit vector pointing in the direction of a given vector, nice handy little formula. This is easy to prove, even easier to kind of persuade yourself intuitively, but very important formula to know, make sure to memorize. This is one of these formulas that once you understand it, I claim you've already memorized it. Right? If you really understand the idea behind this, then there's no effort in memorizing it. So anyway, so make sure to know that formula. And then I'm also going to just throw a couple of quick words at this idea of a component. The idea of a component is that if there is a direction, I made a bad color choice. If there is a direction that you're interested in, described by a vector v, that defines a direction. And if you've got a vector and you say, okay, this vector doesn't point in the direction I care about. Not exactly anyway. Okay, but this is all I really care about. To what extent does the vector I have point in the direction that I want? My metaphor for this is I like to think of the green direction as being, downfield in a football game, right? So you have a football stadium set up, and think about V as being the direction that points downfield, right? Then the component says if the ball starts there and then it ends there, right? So the play begins and then the running back gets tackled there. How many yards did the running back gain? Well, it's not this many yards, right? It's this many yards. Does that make sense to everybody? So that's the idea of a component. Do notice it can be negative. The way I've drawn it here, it's positive. But if this light blue vector were back this way, right? Sacked for a loss, right? And so it can definitely be negative. Okay. All right, so that's the idea of component. I think this is a pretty straight read. Make sure you're comfortable with this argument here. Do the algebra. It's no big. It's basically just trig, right? So flashbacks to trig. You follow through, and you'll get this formula right here. Let's see. Let me do it like this. That the component is computed by that formula right there. Okay, I have a favorite rewrite of this. My rewrite comes from the fact that I look at this and I see, oh my gosh, check it out. V divided by the magnitude of V. Where have I seen that before? Oh, yeah. V divided by the magnitude of V. That's how you make a unit vector pointing in the relevant direction. So that V divided by the magnitude of V is a unit vector. So said differently, a component is a dot product. Oh, I didn't highlight in the right places. A component, let's get rid of that. Component is a dot product. Wrong color again. A component is a dot product with a unit vector. Yes? Oh, okay, yeah, sure. What?
Why use the word component as opposed to projection?
That's a great question, and I'm going to get to projections in just 2 seconds. Yeah. Reasonable question. Okay, so for the moment, we're only talking about components. Components are as described there. Okay, by the way, this is how I think about components. It is kind of handy to have a formula that you can sort of rote memorize, but I want to remind you that's a reflexive, I'm going to say bad habit, right? I don't want to be too judgy, but in classes where the goal is to be able to compute and have an answer and put a box around it, you know the formulas, you rehearse the algorithms, and then you want something you can compute with. And there are moments when we have to do computations. Okay, sure, I suppose, fine. It's a kind of harmless, I suppose, to know this formula. But again, that's not our primary goal here. Our primary goal is to understand ideas, right? And I think the idea is a lot nicer here. Components are dot products with unit vectors, right? And it rolls off the tongue if nothing else, right? This formula, you have to have a conversation. Wait, why do I divide by the magnitude of V? Well, it's because of trig and triangles and complicated story that you're not going to remember as easily, if nothing else. So I like this point of view here better. Okay, what's the deal with projections? Very similar idea. Very similar idea. Again, we have a direction that we're interested in. We have some vector. And we're interested in, not how many yards did we gain or lose, on the football field. Here we're interested in that actual vector. Let me emphasize the distinction. If you come back over here to where we're talking about components, components are scalars. It's tempting to call it a distance. Awkward little annoyance. Distances are intrinsically positive things, right? And so the component does not have to be positive. Component could be negative. It's a dot product. It could totally be negative. So you're going to think of it as being kind of like a distance. It's not necessarily. It is a scalar. You might think of it as a coordinate, if you like. But it's a scalar. A projection is a vector. Does that make sense?
Yeah.
Okay, yeah. So, okay, how do we compute that projection? Well, I observe that I know a couple of things about this vector. I know what the unit vector is that points in that direction, and I know what scalar to multiply by. That's the component. Right? It's a really nice way to think about that. So this is the formula that I remember. This is how I understand how to compute projections. It's, let me just go ahead and, if I can get this thing to cooperate. There we go. Projection is component, dot product of the unit vector, times the direction, namely that unit vector. So that's my favorite way to think about it. Now, I will point out there are other formulas. And for example, you might call it a competing formula, is what you get when you take the unit vectors here and you write them by the little handy-dandy formula we know for how to compute that unit vector. And you kind of work it all out, blah, 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 and it does give you this other formula, and you can use this formula, or you can use that formula. And again, this is kind of up to you. Let's talk pros and cons. This formula, plug and chug. You give me a V describing a direction and a W whose projection you want to know in that direction. Plug and chug. Sweet. This is weirder. You got to compute U first, right? A lot of people like this formula. I'm going to make the observation that, it's not about plug and chug. Again, you've heard me say this many times. You're going to hear it many more. We're interested in ideas, not just plug and chug. Here, the idea is simpler. Component times unit vector, right? This makes sense. You can see this in the picture. This is geometrically natural. Why do you divide by v dot v here? Well, now there's an answer to the question, but it's a bunch of details. So from an intuition standpoint, this is nowhere near as good. And again, you see that tension between what would my middle school math teacher have me memorize, right, versus what actually what connects most naturally with ideas. Okay, yes?
If you're not doing the unit vector, aren't you going to have to do the second one anyway to find what the unit vector is?
No. From a computational standpoint, I don't really care. If you want to know both of these, and if you find this computationally more convenient, yeah, sure, fine, no problem. But you can totally use this to compute as well, because we know the formula for that unit vector. It's just v divided by the magnitude of v. So that's what I like to do myself. Yeah. Right. Okay. All right. Okay. So cross products. This is a long story. We're not going to be able to finish this today. We're going to be able to make some progress. Hopefully, we'll see how well this goes. There's a lot of ideas connected to cross product. Cross product connects very, very powerfully and naturally to determinants. And it connects very powerfully and naturally also to this, what I'm going to call this idea of the geometric order of a list. So this is what I want to start with. We're going to start in 2 dimensions. If you're in 2 dimensions, and if you have 2 vectors in 2 dimensions, specifically ordered, which one's first, which one's second? Right? That's key to the point. We're not talking about a set of 2 vectors. Sets are unordered. Sets are just things in a bag. They kind of move around and, whatever. We're talking about an ordered list. By the way, the word list means ordered, so this was superfluous, but just for emphasis. Okay. So A first, B second. We can talk about something geometric about this list. Let's suppose that whichever vector gets listed first, called A, maybe it's like that, suppose, and whichever vector gets listed second, maybe that's like this, hypothetically, let's just say. Notice that as you go through that list, A first, B second, that suggests kind of a counterclockwise rotation for that list of vectors as drawn on the left there. Does everybody see that? From green to blue, counterclockwise. Okay, yeah, sure. But now, keep in mind, whichever vector was listed, I don't know what that vector is going to be. Maybe that first vector is like this. Maybe that second vector is like this. For this list, now again, still A first, B second. Notice these A and B make that list clockwise, not counterclockwise. Y'all see the difference? Everybody happy with that? Okay. And sometimes it's awkward. Sometimes your first vector and your second vector, maybe they're parallel. Maybe one of the vectors is 0. Maybe the other vector is 0. Maybe they're both 0. Maybe they point in opposite directions or the same direction. Various different cases, but if you think about it, and this is a good exercise, if you think through all the different ways in which neither clockwise nor counterclockwise really makes sense, they're all linearly dependent. How about that? All right. So this is what I mean by geometric order of a list. The order is either counterclockwise or clockwise or dependent. And the cool thing about this, it seems like I just kind of made up a bunch of nonsense, but it's pretty easy to persuade yourself, I think, that if you take a counterclockwise list and if you reflect those vectors over some line, the result will be clockwise. So an easy summary of this is these are mirror images of each other. These notions of clockwise and counterclockwise are mirror images of each other. Likewise, if you trade positions, if you take the first vector and put it second, and you take the second vector and put it first, if you trade positions, that will always change the order of the list. For example. And then I'm going to point out also if you take a list of vectors, if you take that entire picture and you just rotate the entire picture, clockwise is still clockwise, right? If I take my watch, right, the hand is going clockwise. If I do like this, still going clockwise, right? The rotation doesn't change what is clockwise or counterclockwise. Okay. Weirdly, there is a three-dimensional version of this. And it comes with using the human hand. Well, there's different ways to think about it, but a really convenient, I almost said handy, a really convenient way to do this distinction is to talk about right-handed and left-handed. And the rule is like as follows. Let's look at this first picture. Keep in mind we're talking about an ordered list, A, B, C. Arbitrarily, not because of alphabetical order. Alphabetical order doesn't mean anything. Right? But if A is first, B is second, and C is third, we're going to talk about right-handed first. Index finger first. Point your index finger parallel to your palm, like you normally would. Point that in the direction of that first vector. Take your middle finger and bend your middle finger. I'm going to say the way middle fingers want to bend. Please don't get cute, right? None of this nonsense right here, right? You can't bend it backward. No hand yoga, as I like to call it. Bend that middle finger toward your palm. so that it points in the direction of B. Now you might say, hey, wait a minute, what if I had my index finger pointing in the A direction like this? Now I can't make my middle finger do that. Yeah, fine. So rotate, right, in whatever way you have to so that your middle finger bends the way it wants to and points in the direction of B. Is that cool? A and B define a plane. Your thumb will point on one side or the other side of that plane. If C is on the same side of the plane as your thumb, then we call that a right-handed list. Then ABC is right-handed. Now let's look at this second list here. I've called this a left-handed list. I claim that this is not right-handed. I cannot do what I just described with this list. And here's my demonstration. Index finger in the direction of the first vector A. Oh wait, my middle finger doesn't do what it's... Okay, so again, rotate. Now my middle finger will point in the direction of B. Yeah? Look at my thumb. My thumb is below the plane. C is above the plane. I lose. This is not a right-handed list. I just can't do it with my right hand. I can totally do it with my left hand. Yeah? So that's the distinction, right-handed, left-handed. Again, there are various cases where neither is going to work. There's a bunch of them. Good exercise. Think it through. What are the various different cases where neither of these quite make sense? And what you're going to find is that they're all linearly dependent. And these have, amazingly, all the same properties as clockwise, counterclockwise. They are mirror images of each other. Trading changes the order, and rotations don't make any difference. My right hand, still my right hand. Okay. All right. Good place to draw the line. See y'all later. Have a good rest of your Wednesday. See you on Friday.